Hi, everyone, and welcome to the first lecture of the semester, Introduction to Statistics. If you were to pull someone off the street and ask them to define statistics, they are likely to tell you something along the lines of facts or figures, average income, birth rates, crime rates, and things of that nature. For our purpose, though, the definition is more broad. Essentially, statistics are a set of mathematical procedures for organizing, summarizing, and interpreting information. Starting with some basic terms, we have a population, which is a set of all individuals of interest in a particular study. Sometimes a population is large. Maybe you're interested in all children in the United States. And sometimes it's smaller. Maybe you're interested in all students at ISU or all people at a specific company. However, depending on how many people are in the population, you might not be able to measure everyone. Imagine trying to conduct an interview with every single student at ISU. You might not be able to finish that in a year or even 2 years, and then each semester, more students are added. Therefore, we often need to take a sample where we select individuals from that population to participate in the study. And then those individuals represent the population. I like to think of this as being at an ice cream shop and asking for a sample of a particular flavor. They typically give you a little spoon of that ice cream, and then you can say that's what the entire tub tastes like before you order. In other words, we can make what we call generalizations based on a small amount of information available. This figure is another way of visualizing this process. At the top, we have the population of interest, and then we select a sample. That sample participates in the study, and then the results are generalized to the population of interest. In any study, we have a number of variables, which are characteristics or conditions that change or have different values for different individuals. Maybe it's someone's diet, their intelligence, their mood, or maybe their income. I like to think of variables as anything you might be interested in examining. From measuring variables, we obtain data. Data is plural and refers to measurements or observations. For instance, this is a graph called a scatter plot exploring heights and weights for different individuals. Each dot on the graph is one person. Together, these dots are called data. Datum is a singular measurement or observation. If you were to select one dot or one person's measurement out of the graph, that is a single datum point. This is also called a score or a raw score. A data set is a collection of measurements or observations. The example on the slide is of taxes and home prices, and in the data set there is the house name, sale price, size, age, and these are just some of the numbers collected. The list goes on. All of the information together creates a data set. There are two types of statistics we can run on our data, descriptive and inferential. Descriptive statistics are used to summarize, organize, and simplify data. Think about calculating averages or making a graph. Essentially, this helps us to describe the numbers we have. Inferential statistics allow us to generalize sample findings to a population. It allows us to complete that process we talked about earlier, in which we take a sample and infer something about a population. However, when we take a sample, that doesn't mean that the numbers we obtain are exactly what we would find in the population. There is typically some sampling error, which is the discrepancy between a sample statistic and the corresponding population parameter. Essentially, the people we pick might be outside the norm and give us a false idea of the population. Say we try to measure people's feelings about college. Those who really enjoy college might be more willing to participate, and then we might falsely make the assumption that everyone who attends college is happy. We aren't capturing the true average of the population. We can try to minimize this with random selection, where we randomly select who participates in the study, say with a random number generator, but we can't typically get rid of error altogether. We simply try to minimize it. Here is another example of sampling error. Say our population is a small school of 1,000 college students. The population has an average age of 21.3 years, an average intelligence or IQ score of 112.5, and is 65% female and 35% male. Then, say we select 5 people randomly to participate in our study. We get Eric, Jessica, Laura, Karen, and Brian. Together, their average age is 19.8 years. They have an average IQ of 104.6. The sample is 60% female and 40% male. You can see that these numbers are close, but it's not an exact replication of the population. This discrepancy is sampling error. Likewise, we can sample 5 more people: Tom, Kristen, Sarah, Andrew, and John. This group has an average age of 20.4 years, an average IQ of 114.2, and is 40% female, 60% male. Again, because the numbers are not exact, there is some sampling error here. It's close, but it's not an exact reflection of the population. So there are different methods of setting up a study. First is the correlational method, which is when 2 variables are observed to determine whether there is a relation between them. This word relation is important because some people mistake it for cause and effect. We are simply stating that when one variable increases or decreases, another variable increases or decreases. In other words, we can't confuse correlation with causation. A great example of this is the relation between ice cream and sunburns. The data shows that as ice cream sales increase, so do the number of sunburns. But ice cream doesn't cause sunburns, right? Instead, there is a third variable of sunny and hot weather that is affecting them both. Here is another example of a correlation. This graph is one that I showed earlier, showing a positive correlation between height and weight. As height increases, weight also increases. However, adults don't tend to grow taller when their weight increases, right? Likewise, if you were taller, you might weigh a little bit more because there is more bone and skin. But it's not accounting for diets or genetic factors of weight. This relation is important, but correlations typically are only showing one piece of the story. Instead, to be able to determine cause and effect, we need to run an experiment. In an experiment, there are 2 types of variables: independence or dependence. The independent variable is a variable manipulated by the researcher. It is something we add or remove from the study. The dependent variable is a variable observed in order to assess the effect of the independent variable. The example on the screen is of a study with plants, examining if the volume of water increases the days to a plant flowering. Water is an independent variable because it can be manipulated. We can water some plants at the recommended amounts. We can overwater others. Maybe there's a group that's not watered at all. And in the study, it is hypothesized to affect days of flowering. That is, the dependent variable depends on the independent variable. Our studies can look very different depending both on the variables and how they are being measured. One type of variable is a discrete variable, which consists of separate, indivisible categories. And what's important to note is that no values can exist between two neighboring categories. In other words, there's no halfway or partial points. If you flip a coin, you can only get heads or tails. If you roll a die, you can only get a number between 1 and 6. Using the previous example, if we were to measure noise and test scores, noise is either there or it's not. Continuous variables, however, have an infinite number of possible values that fall between any two observed values. Weight is a great example of this. The scale on the slide shows 126.4 pounds. There are many values in decimals for weight, especially if you are measuring more than one decimal place. Height, weight, temperature, and time are also examples of continuous variables. These variables simply have more numbers that they can provide. What we can do with the data we obtain also depends on the scales of measurement we use. Nominal scales label and categorize observations without the ability to make any quantitative or numerical distinctions between observations. Colors are a great example of this. We can easily label these, and while we may have our own favorites, there are no numbers to tell us which color is the best. Or maybe you are labeling things around your house: pencils, pens, erasers. You can tally how many of these things you have per category, but it doesn't tell you if one object is more important or affects anything else. You are simply stating that it is there. Ordinal scales refer to a set of categories that are organized in an ordered sequence. We have observations which are ranked in terms of size or magnitude. So if you were to run a race, we know that the person who comes in first is the fastest, and we know that second place came in between first place and third place. However, we don't have any information beyond that. We don't know how fast each person was. Similarly, you might be ordering a drink and see the sizes of small, medium, and large. And sometimes that large is double or even quadruple the size of the medium, and then the medium is closer in size to the small. We have a clear order with the ordinal scale, but we don't have information about the numbers between the variables. Interval scales have ordered categories that are all intervals of exactly the same size. This means we do know the difference between 1 and 2, or 5 and 10. However, the 0 point is arbitrary. A great example of this is a thermometer. We know that 4 degrees is double of 2 degrees, and we can easily measure that. However, the 0 point is different depending on which measurement system is being used, and temperature can go into the negatives. 0 is just wherever the person who invented the scale says it is. Calendars are similar. The year 0 isn't the start of all time ever. Instead, we have BC or BCE to capture time before we started counting the years in this way. A ratio scale is an interval scale with an absolute 0 point. Think about speed. If a car is going 0 miles an hour, it is not moving at all. We don't have that subjectivity, and it cannot go negative miles per hour. Money is also an example, depending on how you measure it. You either have money or you don't. Here's a summary of the measurement scales put together for your own notes. Pause to review. And lastly, we have some statistical notations. X and Y refer to raw scores. A capital italicized N refers to the number of scores in a population, while a lowercase italicized n refers to the scores in a sample. And if you remember from any earlier math classes, there is a specific order of operations. You always follow this order when solving a math equation. To remember this order, you can remember, please excuse my dear Aunt Sally, where you complete anything in parentheses first, then exponents, multiplication, division working left to right, summation, which we'll talk about on the next slide, and then addition and subtraction, also working left to right. Summation is when you sum or add a series of numbers. It is notated by the Greek letter sigma shown on the screen. If you see sigma x, you simply add all the scores. Sigma x squared means that you square each score, then add all the numbers together. Sigma with x plus 1 in parentheses means that you add 1 to each score and then sum the numbers. If that's squared, then you add 1 to each score and square each individual, then add the squared values. And if there is sigma x in parentheses squared, you add up all the scores and then square the total. And that is all I have for you. If you have any questions, please do not hesitate to reach out.